So what I want to talk about today is I want to talk about sets and subsets, and we're just going to get into some basic definitions and kind of set up some basic guidelines for us to understand sets, and maybe, you know, kind of be able to talk about sets a little bit more clearly and more freely. So what we're first going to say is that a set is just a grouping of objects. All right, so it's just a grouping of objects, and sometimes we can have big sets, sometimes we have little sets. We can have infinite sets that actually are just defined by having a certain quality, and we'll look at one of those. But, you know, basically all it is at its root is just a set of objects. We don't necessarily have to do math on it. So like one set we might look at, we might say something, we have something called roster notation. That is that it gives us every value that's in the set. And so we'll use these curly Q brackets, and we'll say that we've got a set of groups of people at a poker table. So we've got Juan, and we've got John, right? There's two of those, and Susan and Ling. And those are our four people at the poker table. And in this set of individuals, we know everybody who happens to be there, okay? So that's what we might call a roster notation. On the other hand, we might define a set a little bit differently. We might define it and say something that's called set builder notation. And you'll see one of these too. And set builder notation will say something like X belongs to a group. So like we're going to say X belongs to the integers, okay, such that X equals 2K for K belonging to the integers. And so what this does, okay, and we're going to talk about some of these symbols in just a moment, what this does is this actually gives us a description of every element that's in the set, because it turns out that this set actually is infinite. So what we'll see here in the set builder notation is we're going to see, okay, first, actually, let's first go to this one. It looks like a sideways E. That means belongs to. And it says basically that it is an element of this particular set, and this set, by the way, we'll get into this a little bit more here. This set is the set of the integers. Okay, so we have an element X belonging to another element, the integers. We might call this, the integers here, the domain. The domain is a set itself. And then we've got a definition here, and this tells us what X is. So X equals 2K for K belonging to Z. So this is like the description in set builder notation. And it tells us what it is. So what this is essentially the set of even numbers, the set of even integers. Which is an infinite set. So you can imagine why you can't actually write that in set notation. You can't write it in set notation because it's infinite. So we've got to have another way, okay? This line right here, you may have heard me say it, it makes, it is such that. And it basically says those things that have this quality, okay? So what we'll do is we'll say something like this. This is how our set builder notation will be set up. It'll have our variable, whatever the variable is, X belonging to a domain of some sort, or a grouping of objects, then a line such that, and then it'll have the description. And there's the description, okay? And that's our set builder notation. We're going to utilize that one quite a bit too, because that's, like I said, it's going to come in handy for certain purposes. So there are two different kinds of how we might write out sets. And again, just elements. You also might see something called interval notation. And generally, interval notation is really only going to be used for sets of real numbers. And it'll look something like this. It'll either go like -1 to 3, right? That's a half open, half closed. We'll have another one, say -1 to 3, again, half open, half closed. Right? We'll have something called a closed set, let's say -3 to 6. And then we'll have an open set, which we call 4 to 7, for example. Not really as important for what we're going to do. Because we're looking at discrete numbers, we really are more interested in set builder notation and roster notation. Okay? But these ones, they're used for the real numbers. Used for the reals. Now, some important notation for important sets of numbers. So the first set of numbers that we're going to get to, the one that's going to actually show up the most inside of our class, is something called z, and that's the integers. And we've said before that the integers are essentially what we'll do is I'll write them like this: -3, -2, -1, 0, 1, 2, 3, etc., etc., etc. And so those are called the integers. All right, there are no fractions in the integers, so we're only talking about whole numbers and their negatives. 0, notice that 0, right? 0, and here's that thing again, 0 belongs to the integers. The next set, which is represented by, you're either going to see, it's going to look a lot like an N. It's really, it's got to get a different name. It's actually called an aleph naught. Okay? And this actually represents the natural numbers, or what we might call the counting numbers. When we work with sequences, we're going to work with the natural numbers an awful lot. And they're going to start with 0, or not, excuse me, not 0, but 1, 2, 3, and then they go on ad infinitum, up to infinity. So that's the natural numbers. Then we're going to have Q, and these are the rational numbers. And we'll get into an actual set theoretic definition of these in just a moment. The next grouping that we want to look at is something called Q, and that is the rational numbers. And essentially, for our purposes right now, the rational numbers are anything that can be written as a fraction. Anything that can be written as what we call a ratio, hence why they're called the rational numbers. We also have the irrational numbers, but we don't have a particular symbol for them, or I'm not going to use one. And then finally we have this one. This is called the reals. These are the real numbers, and that's the real number line. So those are the big groups of numbers that we're going to be looking at, or going to be using during this course. All right, so now what we're going to look at now is we've got three basic sets of symbols and relationships that we have within when we're looking at sets. All right, so we've talked about how a set is just a collection of objects. Now what we want to do is we actually want to make some distinctions about whether or not an element belongs to a set, or whether or not we have another set is in fact a subset of a set, or we have this other idea of what's called a proper subset. So let's start out with this idea of an element belonging to the set A. And so we're going to say that X belongs to A. And so that's the symbol right there, is X belonging to A. And so let's define A. We'll let A equal the set 1, 2, 3, 4. Okay? So what we can say then, if A is that, we can say that 1 belongs to A, because 1 is an element in A. That's it. Okay? You see, one's in there. That's all. 1's in A. 3 belongs to A because 3 is an element in the set A. Okay? 2 belongs to A, 4 belongs to A. Great. Those are all elements within the set. Now, here's the deal. We could also say, for example, that 5 does not belong to A. There we are. That actually is the statement that 5 is not within the set. Great. Let's take, for example, let's take a look at another example. Let's say B. So we'll have B, and we'll write B in set builder notation. And we'll say X belongs to the integers. Okay? And we'll define it as X equals 2K for K belonging to the integers. And so essentially what this is saying is it's just saying these are the even numbers, the even integers. Okay, we got those even integers. And so, for example, 2 belongs to B, excuse me. And we've also got that 24 belongs to B because 24 is 2 times 12. Okay, 12 is an integer. Also, 24 is an even number if you kind of want to think from that perspective. But we have, say, for example, -1 does not belong to B. -1 is not an even number, so -1 is not within the set. It doesn't belong. And so what you see here is that's what that element, that means. That means that there is an element, okay, called 2 that is in the set B, or the element 2 has the qualities and characteristics of every element in B. Okay? And that's what we mean by belonging. That's the idea of belonging. Now what we have next is we have the idea of subset. And so let's say, for example, and the symbol for subset is like this, okay? And so what we're going to say is, say, for example, that we'll choose and we'll create a set C. And so C is going to equal the set 2, 3. Notice that C is a set. C is, yes, it's a collection of elements, but C is itself a set. Those little curly Q brackets, they actually define that that thing is a set. So notice that the elements that are in C are also in A. So what we're going to say is that C is a subset of A, right? And I'll write that down. C is a subset of A. And how we would write this out in logic, if we want to write it out in logic, is if X belongs to C, then X belongs to A as well. And that's what it means for C to be a subset of A. Okay? Let's take, for example, we'll look at another one. Let's look at D, and let's say that D is the set -2, 0, 2, 4. Now D is not a subset of A because -2 does not belong to A. So basically what we're saying here is that our set D cannot be a subset of A because there's an element in A that's not, an element in D that's not also in A. Okay? Again, we have to have this relationship. If X belongs to that first one, X also has to belong to the second one. That has to happen, right? Logically speaking, that's what's got to happen. Well, in this case, we've got an element -2 that does belong to D, okay, but does not belong to A, so we don't have a subset relationship. On the other hand, what we do know here is we know that D is a subset of B. Notice that every element in D is an even number. So since every element in D is an even number, that means that D is a subset of B. Okay? Because, again, if we want to write it in logic, we're going to write X belongs to D implies X belongs to B. All right? So to have the subset relationship, all right, what we have to have is we have to have every element within the set be contained within the element on the right-hand, the set on the right-hand side. Okay? Just a distinction here, just to make something very clear as to a distinction mathematically. We'll move this down a little bit. Is -2 is not a subset of B. And the reason why is because -2 is not a set. When we're talking about sets and subsets, we need to make sure that we are talking about a set being a subset of another set. Okay? If we're looking at elements, we can talk about elements belonging to sets. That's a key distinction there. Okay, so now the last piece here that we want to get, and then we're going to get into some details that are going to kind of be important, is this idea of a proper subset. So the symbol for a proper subset is the subset sign, but it doesn't have that like line underneath. And I kind of think about it in terms of the less than or equal to kind of sign. What we want to get with the proper subset is that it's actually a stronger condition. And in mathematics, we oftentimes talk about weaker and stronger conditions. That is that whenever we have more items inside of one grouping, right, that's a weaker condition. It allows more things in. That's weaker. And then a stronger one is one that says that restricts the grouping a bit more. So when we talk about the proper subset, right, what we'll do is we'll say that A is a proper subset of B. Okay? If and only if, and we're going to have two conditions. Okay? X, for all X belonging to A, we have that condition that X belongs to A implies that X belongs to B. That is that every element that's in A also belongs to B. And what we have to have as well is there exists an X belonging to B such that X belongs to B, okay, implies that X does not belong to A. So there's got to be at least one element in B that's not in fact inside of A, right? B's got to be the bigger set, and that's really the idea. B is the bigger set in some ways. Now, when we talk about infinite sets, sometimes we're calling something bigger and smaller. It doesn't quite make the same amount of sense, but that's kind of the idea. Like, the set A is going to be enclosed fully into B, and there's stuff outside of it, okay? If I were to draw something in terms of like a Venn diagram, we might imagine that here's B, okay? And here's A, and A's within B, and then there's at least one thing outside of here. We'll call this our little X. X is outside of A, but it is inside of B still. Give you an example. Let's say that A is equal to 1, 2, 3, 4, and we'll have that B equals, let's have just B be equal to the set of integers. So B is equal to the set of integers. Now, notice that 1, 2, 3, and 4, they're all integers, right? And so consequently, A is in fact a subset of B. We know that already. And if you think about it, say for example, we'll take 5 belongs to B, but 5 does not belong to A. So there's at least one element that's in B that's not in A. So consequently, A is a subset, proper subset of B. It's a proper subset of B. Okay? We can think about some other proper subsets of B as well, since B is the integers, like say all even numbers. Okay, so if we take C equal to the set of all X belonging to Z, such that X equals 2K for K belonging to the integers, so since we have that set is everything in there is inside of the integers, but we have things like 3, -27, 5, 11, odd numbers that are not actually in C, because C is all the even numbers. So what we can say is that C is a proper subset of B. And there we go. Okay? And let's talk about why this is important. This is important because for this reason. This actually allows us to define equality. So our proper subset idea actually allows us to define equality. All right? Let's say, for example, we have two sets. We have set A and we have set B. Okay? Set A and set B. And let's say that A is a subset of B, and then strangely enough that B is also a subset of A. So everything in A, every element in A is in B. And every element in B is in A. So if we think about that for a second, that means that A and B have to be the same. Okay? A and B have to be the same. So we'll define equality this way. A equals B if and only if A is a subset of B and B is a subset of A. And so essentially we're saying that if it's in B, it's in A, and if it's in A, it's also in B. And this allows us to actually say that we have equality. Okay? So like for example, and it kind of seems obvious, but it ends up becoming really important when we do proof, we have A equals 1, 2, 3, okay, and B equals, again, 1, 2, 3. And you're like, well, that's obvious. A and B are exactly the same. Okay, great. A and B are the same, right? X belongs to A implies X belongs to B. It's true. Go ahead and take a second. Think about that. Pause if you need to. X belongs to B implies that X belongs to A. Also true. You can sit down and think about that for a minute too. Totally going to be true. It's going to end up being true. Okay. So x belongs to A if and only if x belongs to B. And so this is another way for us to define equality, is that if x is in A, then x is in B, and if x is in B, then x is in A. That ends up becoming a biconditional. And that ends up giving us equality. What's going to be kind of interesting is you'll say something like, okay, well, let's look at an example. Let's say, for example, I have the set of all x belonging to Z, okay, such that x, or x is greater than or equal to -1 and less than or equal to 1. So all the integers there. So that's the set -1, 0, 1. Well, you might actually want to say, so let's say A equals this, and we have B, we'll actually write that in roster notation, -1, 0, 1. Okay? So those two end up being exactly the same. A equal to x belonging to Z, -1, less than or equal to x, less than or equal to 1. And B is just -1, 0, 1. Well, what you might want to do is you might want to actually say, well, does A equal B? And if you think about it, yeah, they do. I mean, it's kind of obvious in terms of it's a finite set, all right? But, you know, the way that you're going to prove that is you're going to prove that every element that's in A is also going to be in B, and every element in B is also going to end up being in A. And that's actually how we define equality. And that's going to become the foundation for equality when we start talking about things like the equality of the real number line, right? We might talk about the set of all solutions to a particular math problem. Well, how do you know that the set of all solutions to the math problem is in fact the only set of solutions? It's essentially this, right? We actually show that those two sets are in fact the same. So now the last thing that we want to get into is this thing called the empty set. So the empty set is a set with no elements in it. So we're going to define that it's going to be like a 0 with a line through it. That's going to be the thing called the empty set. It is a set with no elements in it. Inside of computer science, you may see it, say for example, as being written something like this, like in Python, right? There's an empty set, or you might also see it somewhat like this, where we have an empty set of brackets. There's nothing in there. There's no elements in there, okay? There is no elements. There are none, right? It is empty. It's like a container. You imagine you've got this container, and inside the container there's nothing in it, and that's your empty set. Now, the reason why the empty set is important for our conversation is that it turns out that the empty set is a subset of all sets. Okay, it's going to be a subset of all sets, all right? And the reason why is that, like, if we look at this, remember that our definition was x belongs to A implies that x belongs to B. Well, if we think about the empty set, so we'll let A equal the empty set. And if we let A equal the empty set, we got x belongs to the empty set implies that x belongs to B. Well, this statement here is always false. That statement is always false, okay? And if you remember when you talk about logic, from the perspective of logic, if you have false implies true, or even false implies false, the conditional is still true. Conditional is still true. So basically what that's telling us, in fact more than basically, this is exactly what it's telling us. It tells us that in fact, trivially, and when we talk about trivially, this is really what we mean by trivially. Trivially, it's always true, that the empty set is always a subset of every set. So, for all sets B, the empty set is a subset of B. Great. And notice that it's going to be, I did not use the proper subset phrase. What we need to get is that when is it the case that we actually have the proper subset? Well, if B is non-empty, so if B is non-empty, then we can actually say that the empty set is a proper subset of B. It's a proper subset of B, and that's because since B is non-empty, B actually has an element in it, and that element then is not in the empty set, okay? So x belongs to B, okay, and x is actually an element, but x does not belong to the empty set because the empty set is empty, so consequently we have that proper subset condition, okay? And that's the idea. So the empty set is a proper subset of B. Well, you might ask yourself, well, when is it the case, right, that the empty set is just a straight subset of B when it's not a proper subset? So when is the empty set not a proper subset of B? All right, so it's always a subset, but when is it not a proper subset? And if you think about it for a second, pause for a second, well, it's when B actually equals the empty set, okay? So there's our question, and that's when B equals the empty set. Trivially speaking, that the empty set is always a subset of the empty set. It is not a proper subset of the empty set. All right, you know what? You got to think about these for just a minute. Look at the definitions that we've been using, because the definitions will lead you towards this conclusion, right? But for right now, the only time that we're going to have the strict subset, but not a proper subset, is when our B set, our right-hand set, is actually the empty set itself, okay? Quick overview for that empty set. One, it's a set with no elements, right? So there's nothing in it. Some things that we want to get is that that empty set is always a subset of every other set, okay? And it is frequently a proper subset of our set B, but it is not a proper subset if B actually is the empty set itself, right? And so that kind of gives us a little bit of an overview for the empty set. It's going to actually end up being really important when you're talking about things like power sets, or in fact when you're kind of like looking through and you're developing, say for example, programs or algorithms, and you want to get to the point at which, you know, like, okay, is there nothing in the set any longer, right? My set is empty, and you want to actually get the idea that, oh yeah, that nothing's left in the container. All right, so let's review. One of the reasons why I want to do this is that oftentimes with sets are just one of those disciplines where you just it's got a lot of definitions and you're just matching things to definitions over and over and over again if you're working in sets, right? So we'll start out with one. A set A is a collection of elements. That's all it is, just a collection of elements. Two, the cardinality of A is the number of elements in A. So we can count that many. Should state that the empty set has a cardinality of 0 because there's nothing in the empty set. 3, the element X belongs to A. X belongs to A if X is contained in A. That is that if the element is X is in A, then we say that X belongs to A. That's another way to state it. Number 4, we got A is a subset of B if and only if for all X, X belongs to A implies X belongs to B. So if X is in A, we have X also in B. That's the idea of a subset. A proper subset is a little bit stronger. We have this AND statement. So again, we have for all X, X belongs to A implies X belongs to B. And we have at least one X. There exists an X such that X is in B, and we should actually add, there's an AND in here. We'll add that AND. And that X is not in A. So the empty set is the set with no elements. And I think I actually prefer this. I couldn't find a symbol, but let's do that and we'll remove the negation. So we're basically to say X belongs to B and X does not belong to A. And finally 6, we have the empty set is the set with no elements. The empty set is a subset of every set, and that's something important that we want to remember.